Hi guys, and welcome to the video on the fundamental counting principle. So for this video guys, we're going to learn to calculate the number of options that make up a sample space. We're doing this so that we can quickly be able to calculate probability with multiple differing outcomes. You will know you're successful when you can calculate the number of outcomes in a sample space using this method quickly. So let's get started. First, we got to know what a sample space is. So, a sample space is the set of all of the possible outcomes in a probability experiment. So, quick example of this is two coins are tossed. What does the sample space look like for this experiment? I can list out all the different outcomes, and I can follow this tree here. Okay, heads, heads. That's one of the outcomes, and then I flip a heads and I get a tails. So, heads, tails is an outcome. Or I flip a tails first and then a heads. That's a tails, heads outcome. Or tails, tails. So that would be another outcome, leaving me with 4 unique outcomes. And here's a table wave representing it, and that's a list wave representing it as well. The fundamental counting principle is the guiding rule for finding the number of ways to accomplish 2 tasks. So when I say 2, I mean 2 or more. But if there are m ways to do one thing and n ways to do another, then there are m times n ways of doing both. So we can multiply even more choices out together. We just keep multiplying them off. So you would have the number of options in here. So m ways to do C1 times n ways to do C2 times O ways to do C3 and P ways to do C4 and so on and so forth. So you just keep going on and on and on for however many different choices we need to make. So you can track those outcomes with a tree diagram to represent each choice being made. So here, what's happening is in my initial thing, I'm making a coin flip 3 times. So you have coin flip 1, you have coin flip 2, and you have coin flip 3. So there are 2 ways here to do for coin flip 1 to happen. So coin flip 1 has 2 ways to occur times 2 ways for coin flip 2 to occur times 2 ways for coin flip 3 to occur, which means that there are 8 unique outcomes. So there are 8 different outcomes here. So if I wanted to calculate the probability, for example, of getting like 2 tails, then I would look for all of the ones where I have at least 2 tails show up. And then I could go ahead and I could put that over 8 in order to calculate that probability. So we're just going to get right into some examples with this one. Because that's pretty much all you need to know about this. A sandwich shop offers a lunch special where you can combine a soup sandwich and drink for $8.99. The shop limits the choices to 2 soups, 3 sandwiches, and 4 drinks. Draw a decision tree and then calculate how many different combos are possible for the lunch special. Okay, so what we're going to do here is we're going to start, and we have to make a choice. We've got 2 soups, so we have to pick a soup. So we can have soup A, or we can have soup B. We don't know what the soups are. Okay, after soup A, we can go ahead and we have 3 choices that we have to make. So then we'll do this way too. I'm going to erase and redraw those. The next choice we have to make is a sandwich. So we either have sandwich A, we either have sandwich B, or we have sandwich C for both soup A and soup B. And then we have 4 different drinks, so we still have to pick our drink to complete the special. So I'm going to need actually a ton of different room. You kind of can already see how big this stuff gets, the decision trees. So I'm going to move that down and I'm going to ungroup this to give myself a little bit more space here. Not rotate, going to drag these down. Okay, the next thing off of A is there are 4 different drinks. We have drink A and drink B, drink C, and drink D. So you can kind of already see that we have a ton of different choices. And you know what's going to happen is it's going to be the same thing coming off of B, coming off of C, and then this way too. So there's going to be 4 here, 4 here, 4 here, 4 here, and 4 here. So what we can do then is use the fundamental counting principle, and we can say we've got 2 soups times 3 sandwiches times 4 drinks. And when you do that, 2 times 3 times 4 gives you a total of 6 times 4, or 24 combinations. So we have 24 different combos that we can make for our lunch special. Okay, a quick reminder, guys, that anytime you do 2 different experiments and you want to know the number of outcomes between them, you are multiplying the total outcomes for one by the total number of outcomes for another. So example, and one of the most common ones that I see is that 2 dice are rolled. That means that there are 36 because there are 6 outcomes for the first die. So die 1 would have 6 outcomes, and die 2 has 6 outcomes as well. So you are going to multiply that together to be the total number of outcomes, or 36. Another example might be you flip a coin. So if you flip a coin and roll a die, that would mean that you would have 6 times, or excuse me, in order. I want to do it in order so we don't get confused. You're going to have 2 times 6 different outcomes, or 12 outcomes. 2 for the coin and 6 for the die roll. So let's extrapolate this into some examples. If Mr. Wirtz has 6 pairs of khaki pants, 10 polos, and 4 pairs of socks, how many unique outfits can he wear? So I have to make some choices here, okay? I have to pick a pair of pants. I have to pick a polo. So I've got choice 1, I've got choice 2, and I've got to pick some socks. Just for the record, guys, I definitely have more pairs of socks, polos, and khaki pants than that. Okay, so there are 6 pairs of pants. I have 10 different polos, more than that, and then 4 pairs of socks that I can wear. So in this particular case, I need to multiply all my choice amounts together. So it's going to be 6 times 10 times 4, or 60 times 4, or 240 outfits. So there are 240 different outfits that I can wear with that amount of clothes. So suppose that the set of a license plates has any 3 letters from the alphabet, followed by a string of any 3 numbers. So in Wisconsin, we used to have a license plate system where they did a letter, followed by a letter, followed by a letter. So actually, I'm going to rewrite that. They did letter, 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 dash, number, number, number. Give you an example. It was actually reversed, but I can't quite copy Wisconsin's. I'm not supposed to just copy the license plate formula. So like example in Wisconsin that you might see would have been you would have done a letter like 725 A V D. That used to be the license plate system in Wisconsin. So how many different license plates are possible? And we're not going to answer, or we are going to answer letter B for a second. So first, let's calculate how many different ones are possible. So there are, for the letters, 26 times 26, according to the formula, times 26. unique letters. Okay, so letter 1, there's 26 letters available. Letter 2, there are 26 letters available. And letter 3, there are 26 letters available. And then you have the numbers. There are 10. 0 through 9 is 10, 10, and 10. So we're going to go ahead and move those down here, actually. And you're going to multiply those because you're going to choose times a number. The first number pick, the second number pick, and the third number pick. So you go ahead and multiply all of those out, okay? And you would get 26 times 26 times 26 is 17,576. And then 10 times 10 times 10 is 1,000. So you're going to multiply that by 1,000. And the total number of license plates that are available using this system is 17,576,000 plates. Now, I do want to say that the government does not use, okay, so remember, the government does not use, usually does not use I and does not use O. So this would actually be 24, 24, 24. But the problem doesn't actually say anything about that. Usually the government, though, doesn't use I and O because I and O look like 1 and 0. And so in order to cut down confusion, they do not use I and O unless those are printed on like vanity plates. So then what is the probability that the license plate has no repeats? So we know that there are, remember, probability is total outcomes on the bottom and the favorable on the top. So we need to calculate the favorable because we already know the total outcomes. So the probability would be favorable over total. We do know that the total is 17 million and then 576,000. What we do need to calculate is the probability that a plate has no repeats. So I'm going to scroll down just a little bit. In order to calculate, we're going to still take that formula of L1 times L2 times L3. It doesn't look like it's going to work for me to copy paste it. So I'm going to have to rewrite it really quick. So you have L1 times L2 times L3 times number 1 times number 2. I'm going to use N instead of the number symbol. What we have to do then is consider that once we pick a letter, it's gone. So for the first letter, there are 26 picks. Then there are only 25 different letters left because we've already picked one, times 24 letters left. And then number-wise, we can pick 10 for the first number. And then we've picked one of them and we can't repeat it. So there's only 9 left. And then we've picked 2 of them and we can't repeat any of those. So there's only 8 left. So we're going to multiply these together. So 26 times 24 times, I did that wrong. 26 times 25 times 24 is 15,600 times 10 times 9 times 8. 720. So you're going to go ahead and multiply 15,600 times 720, and that is a total of 11,232,000. So that is going to be the number of license plates that contain no repeats, which is our favorable outcomes. So then what we're going to do is divide those two. And the probability is approximately 63.9%. So you have a 63.9% chance of getting a license plate where not a single letter nor a single number is repeated on the license plate. So, another example. You take a survey with 5 yes or no answers. How many different ways could you complete the survey? So remember, for choice 1, you have 2 choices. And then choice 2, you have 2 choices, yes or no. And then yes or no again. And then it's kind of going to be the same thing. Choice 3, you have 2 choices, yes or no. Choice 4, you have 2 choices again. Oh, that was a horrible 2. You have 2 choices, yes or no. And for the 5th question, you have, again, 2 different choices, yes or no. So you're going to multiply 2 times 2 times 2 times 2 times 2. And that's the same as doing, that's the equivalent of doing 2 to the 5th power. So if you do 2 times 2 times 2 times 2 times 2, or 2 to the 5th power, you're going to get 32. So there are 32 different ways you could answer this survey. So again, we took the fundamental counting principle, and then we can exponentiate it in order to do it a little faster. And then finally, a company puts a code on each different product they sell. The code is made up of 3 numbers and 2 letters. How many different codes are possible? So this is kind of like the license plate one. The code is made up of 3 numbers. So we have a number, and then we have the next number we have a number, and a number. And then we have a letter and a letter. So there are 10 choices for the first number, 10 choices for the second number, 10 choices for the third number, 26 choices for the first letter, and 26 choices for the second letter. And so we're going to multiply all of these together. For the first 3 tens, I'm going to get 10 times 10 times 10, which is 1,000. And that's going to be multiplied by 26 times 26, which is 676. So that gives me a total of 676,000 codes. Okay. And that's it, guys. Remember that the fundamental counting principle is used to calculate the number of outcomes in a sample space by multiplying the total number of available choices by each other. We can represent this with a tree diagram. The tree diagrams are only for like when we have very, very small sample sets, because I would never expect you to do something like a license plate where you could calculate out the 17 million different branches. That's way too much. Remember that when you want to find your total outcomes, you're using multiplication of outcome totals, not addition. So the biggest takeaway here for that is that if you have 2 die rolls, there are 36 outcomes, not 12. So that's it for today's video, guys. Thanks for watching, and I will see you in the next one.